All right, hello everyone. It is Friday, which means that it's time for our weekly studio review. This week, we're covering what is considered by many to be a conceptually tricky topic. We're going over the topic of recursion this week. So in studio, we have you writing, I believe, 4 different recursive methods, which is what I'm going to cover today. And then actually on the assignment, you'll also be writing a handful of recursive methods, and there's actually, some intentional overlap between those two, which I may discuss a bit as we go on through the problem. So let's dive right in. For many of these problems, we actually gave you a solution to them using loops. Remember that recursion and loops are 2 tools that we have to accomplish the same thing, which is repetition. So for many of these problems, if you take a look at, for example, the very first problem, which is geometric sum, we have this loop version, so we can try and figure out how we might convert this into a recursive version, or at the very least, consider that this is the repetitive part, right? Computing the sum is the repetitive piece of this, so this piece is what's going to have to be done recursively in our solution. So then the other thing to consider is that every recursive method has 2 pieces to it. There's the recursive step, so the method must call itself. That's how we actually achieve the repetition, but then we also must figure out how to stop. We call that the base case. So what is the base case? The instructions have you work through a few examples, and then notice that for this particular problem, we always know that the last term is going to be 1 over 2. In fact, there's actually a pattern here where it's, 1/2 to the 0th power, 1/2 to the 1st power. I'm sorry, this would be 1/2 to the 1st power. Sorry about that. 1/2 to the 2nd power, 1/2 to the 3rd power, 1/2 to the 4th power, and so on and so forth. So for whatever value we are given for n, we know that we're going to be actually kind of working backwards, where this loop actually kind of works forwards. It starts with that first term of 1/2 and then works its way forwards. With recursion, we're going to do it a little bit backwards from how the loop does it. We're going to stop when the power is 1, because we always know that if I give you a value of 7, well, I'm going to eventually end up at 1. If I give you a power of 12, well, eventually I'm going to end up with a power of 1. That's going to be included as part of every computation that we do for any value, any acceptable value of n. So with that in mind, let's go ahead and start trying to piece this recursive method together. We actually kicked it off for you. We helped you out. I'm going to code the base case first. So if n is equal to 1, actually we could take that as, we could say if n is equal to 1. You actually could do if n is equal to 0 as well, return 1, but actually I think this is a better base case for us because the 0th term actually isn't included in this geometric sum series. So we do need to stop at n is equal to 1. This will be our base case. And with the base case, this is a known value. So we just say what the value is. The value for n is equal to 1 is just going to be 0.5. That is the answer. That is the geometric sum for n is equal to 1. Otherwise, if we get here, we know that n must be greater than 1. So we're going to do recursion. This will be our recursive step. How does this work? Well, we have to call the method. That is what makes it recursive, in fact. We have to actually plug in a parameter here, and we need to make sure that as we repeat, we move closer and closer to the base case. So if n plugs in as 7, I can't just put n here again, because then I would stay on 7 forever. The next time I call the method, n would still be 7, still be 7, still be 7. We need to work our way closer to the base case, where n is equal to 1. So to compute the next term in the series, I'm actually going to subtract 1 here. That's part of the solution that needs to go here. We haven't actually done any summing anywhere. So you'll notice this is called a geometric sum. So we actually have to compute this term for the given power. So we'll say math.pow of, oh, I didn't want you to delete all of that, 0.5 to the n power plus this result. And then last, we need to make sure that we return this. We say that this is, in fact, the answer. I believe that this will be a satisfactory result, although we did give you some tests, some unit tests that you can use to check your work. So let's go ahead and run these unit tests, make sure that we see, hopefully we'll see the geometric sum test pass. Actually, they did want us to do geometric sum of 0. Okay, so that's fine. I'll update my base case. I should have done it this way the first time, I suppose, huh? Geometric sum of 0 would be, it says it wants it to be 0. Okay, will do. Let's try and rerun these unit tests now that I've tweaked my base case. We can actually see, before I do that, that all of these other ones for values that aren't 0 did seem like they worked okay. So now that I tweaked my base case, I see that all of the recursive geometric sum tests are, in fact, passing. So we've done it. And the nice thing about that is that this is working very similarly to the way that the iterative version is working. We're just kind of moving in a slightly, from back to front instead of front to back. We can even prove this by debugging. In fact, I'm going to go ahead and set a breakpoint right here and run these tests again. We'll eventually get to the point where we're going to run our recursive method. Let's find an interesting value for n. So for the value of n is equal to 0, that's not very interesting. I'm going to click the resume button until we get to an interesting value of n. Alright, so here's a simple case for where n is equal to 3. Let's walk through this code and make sure we understand the recursive process. Over here on the left, we can see that, alright, the method that we're working with is up at the top. You may notice that there's a lot of other stuff here too. You can ignore that, right? I know that this looks confusing, maybe even a bit intimidating. I'll be honest with you, I don't even know what all of this stuff does. It's not important. What matters to us is right up here at the very top of the method call stack. This is our method that is currently being called, and we can step through. So for the value of n is equal to 3, we haven't hit the base case yet, so we'll go ahead and jump down to the recursive step. That tells us that we need to call this method again, this time for n is equal to 2. So if I step into it, we'll see that, okay, we now have another version of the method on top of the stack, and over here it tells me that n is equal to 2. Well, that's still not our base case, so we'll go ahead and step through and realize that, okay, we're going to call the method again, and n is now 1. Still not our base case, so we'll call it one final time, and we'll get to our base case value of 0, just as we would expect, but we have to work our way back up. Remember that getting to the base case is just half the battle. We now have to work our way back up. We actually haven't done any arithmetic yet. It's actually fairly common for the arithmetic to be done not on the way down to the base case, but on the return trip, on the way back up. So as we proceed back up, we'll see that this first base case is going to return 0. There's the 0 right there. It's now going to compute this term, which should be 1/2, and add it to our 0. So the next time we click the button, we'll see 1/2. It'll then compute this term, which should be 1/4, and add that to our sum, which we see there. And then finally, this is our last step. So it should say it should add 1/8, and here we can see is our final result of 0.875. We already know that result to be correct. We've already run our unit tests and verified that this is going to work. All right, let's move on to our next recursive puzzle. We're next going to do a recursive drawing application. I actually did a recursive drawing problem in class on Monday. The graph paper example is an example of doing some recursive drawing, and it's not that much unlike this one. Notice that we have a big circle here in the middle, and then from there we have four smaller circles, one going up, one going left, one going right, and one going down. This is an example of a divide and conquer problem. Anytime you see the pattern going off in multiple directions, that's a big clue that this is a divide and conquer problem. And once you know it's a divide and conquer problem, that actually gives you some information. We know that there's going to have to be one recursive call for each of these 4 different patterns. So there'll be one going up, one going down, one going left, and one going right. Let's take a look at the code that we've been given to start here. Circles upon circles. The inputs that we have are the center of the circle. We have the radius of the circle. And then this is our minimum drawing threshold. This is actually what we're going to be using for the base case. So we're essentially, we're kind of giving you the base case here. We're saying if the radius is less than the radius minimum drawing threshold, we can simply return. We're done. There's no more work for us to do. This is our base case. This is often going to be the base case for drawing style problems. For drawing style problems, we almost always start with a big version and then draw smaller versions, and then we keep drawing smaller and smaller versions until the versions get so small that it's not even worth drawing them anymore because we can't see them on the screen anyway. So with recursive style drawing problems, your base case is almost always going to be based on the size of the drawing that you're making. There are exceptions though, so it's important to read the problem and make sure you're actually solving what's being asked of you. If we don't hit the base case, then we have some work to do. We need to draw the circle at this position with this radius, with this center position, with this radius. So that's going to be called a standard draw. I think it's just called circle. And you can see it does a pretty good job of guessing which ones I want, except for I actually want this one. Once that's finished, we then need to do our next 4 patterns. And notice that the center position is going to change for each of these, right? In fact, the center is on the circle itself, so we're just shifting the center point of the next drawing up by a radius, or left by a radius, or right by a radius. Those are going to be our 4 recursive calls. You'll see one for each of the 4 directions. Let's start with the one that's going up. We'll call the method circles upon circles. The center position, since we're going up, that's going to affect the y axis. So our y center will go up by the radius. And then the radius itself, does it tell us exactly how the radius changes? It says we divided the radius by 3 at every level. Okay, so we're going to shrink our radius by 3. And then we also have to include this minimum drawing threshold so that we know when we hit the base case. I'll go ahead and paste that in. And I believe that's going to do it for our upper circle. But to check that, we can go ahead and run our circles demo app. It won't be complete yet. We've got a few more that we need to do. But let's just make sure the first one works. So here's the first expected image. That one actually works. If we continue, we see that, okay, I only have the one that's going up. I don't have the other 3 directions, but we'll get there. And so you can see it keeps going up. That's good. Keeps going up. So I believe the up direction is working. Let's do the down direction next, since that's actually going to be a very straightforward change. We're just going to subtract the radius here. And then for the left and right directions, you can think, well, those are also going to be very similar looking recursive statements where we're simply modifying the x-axis instead of the y-axis. So I'll add a radius here. That'll take care of the rightmost direction. And then I'll do this one more time, subtracting the radius, and that will take care of the left direction. And now that we have our 4 recursive calls, remember this is a divide and conquer problem. That means that I called the recursive method 4 times, once for each of the smaller versions of the problem. So now that I have my 4 calls, let's run that demo app one more time and see if we get the proper results. All right, first result still looks good. Second result looks good. Oh yeah, looks like we're doing just fine. Cool. Oops, expected image not available. Well, it's still going. I don't know where those images went, but that's okay. It just keeps going until you give up. That's why those images don't exist. They never did. Okay. I believe that's going to do it for this problem, for this divide and conquer problem. Let's move on and take a look at the next problem. We're now going to be reversing an array. So we're going to take in an array and we're going to reverse it. We're actually going to switch it back. So what was in the front is going to be in the back. What was in the back is going to be in the front. Now, a lot of times when using arrays with recursion, we're going to need something called a helper method. And this is actually an example of when we would need such a helper method. Before we dive in, let's take a look and see. We gave you an iterative version. So take a look and see, right? The first thing we did is we created a new array. And then we're checking the length of the array to make sure that it's greater than 0. These are things that all need to just happen once, right? These things don't need to happen more than one time. We're then going to go in and for every position up to halfway through. We only have to go halfway through because what we're actually going to do is we're going to swap. We're going to swap values. So we can actually use this as our base case for recursion as well, just like we did last time. But we're going to need a helper method. Remember from our discussion in class, the helper method is used to separate the repetitive stuff from the non-repetitive stuff. So anything that just needs to happen one time, like this code right here, that's going to go in our non-helper method, our non-recursive method. And then the stuff that needs to be repeated, like this stuff right here, swapping the indices and stopping at the base case, those are going to go in our helper method. And that's the one that's going to be recursive. The advantage of doing that is, well, A, that separation is good, right? The repetitive stuff is separate from the non-repetitive stuff. But that also gives us the ability to use additional parameters with our helper method to allow us to accomplish more with our methods than if we just tried to cram it all into one method that did everything. Let's go ahead and start coding this up, and I'll try and illustrate where those things come into play. First step, we're going to do all the stuff that needs to happen once in the non-helper method. Actually, I'm going to go ahead and do the definition for the recursive method as well. And think about, for now, I'll keep the parameters the same, but as we go on, actually, no, I'm not going to keep the parameters the same. One of the nice advantages of using a helper method is I can add additional parameters here. And actually, just like the helper method we saw in class, one of the common things to do here is add on the index so that we can see where we are at. In fact, this ends up being pretty critical because the recursive part of the statement is going to be, the base case is going to be to stop once we get to halfway through the array. I'm getting a little bit ahead of myself though. Let's go back to the original version of the method, and I said that stuff that happens once goes here. So I'm going to go back to the iterative method and see that, okay, this stuff all happens just one time. All of this stuff actually happens just one time. So I'm going to take all of this stuff that happens just once, it doesn't get repeated, and I'm going to go ahead and copy it in here. This is where we also need to kick off the recursion. So if I make it to this point, I need to now try and replicate what's happening in this loop. But remember, we're using recursion to do that. So we're going to call our recursive method. We'll say return to reversed, and we'll pass in the array, and we're also going to pass in probably just the current index, right? Probably just that current index of 0. Why are you upset with me? Oh, because I forgot the brackets for my if statement. I thought there was something wrong with my method call. It's actually I just forgot the brackets. We actually haven't used this term yet, and that's okay. I'm not sure we actually need it. Let's go ahead and switch our focus now to the recursive helper method. Starting with the base case. I almost always like to start with the base case. We're going to stop when the index gets more than halfway through the length of our array. So if the index is greater than array.length, then that's when we're going to stop, because we know that we've swapped all of the back values with the front values at that point in time. What about the actual middle of the array? Oh, I need to divide that by 2. What if we're exactly halfway through is kind of what I'm trying to think about as well. So if the array is 10, and that would make the halfway point 5, but that's actually more than halfway. So I actually think this should be less than or equal to be strictly correct. If that's the case, we're done. We need to return our result. However, we have a little bit of a problem with doing that in this point in time, because we've been given the original array, which we're going to be reversing. However, the instructions say that we should not modify the given array itself. We should actually just we just need to create a new array that's going to store the results. We actually did that here, then we never actually did anything with it. I think we actually need to add a third parameter here. This is our original array. We don't want to modify that one directly. We want to create a copy of that array. So I'm going to say int result and I'll pass in this result here, and that's actually what we're going to use oh, it's going to say reversed. That's fine. And that's how we're going to keep track of the result. And that makes our base case solvable. So once we get here, there's no more work to do. We're done. We're just going to return the result. If we aren't done yet, so if the index is less than halfway through the array, then we need to do the swap. And I'll go ahead and come up here and borrow this code. I think we can actually borrow it directly and paste it right in. We do need to know what the last index is. Oh, we had a line of code for that though. That's this line right here, which we can paste in here as well to resolve those errors. And this one, I changed the name of it to result. That's why that's unhappy. But okay. What else do we have that it's unhappy about? I think we're actually getting pretty close to finished with this one. We just need to continue the recursion. So if we need to keep going, then I need to call the method again, plugging in the original array, the result array, and then we're going to bump the index up by 1. All right. Up here, this method is angry because it's saying, what happens if the array length isn't greater than 0? What's the answer going to be? So we need to say what the answer is if this if statement is false. And that would just be an empty array, I would think. So I'll say return reversed, something like that. Should solve that problem. And we're finally at the point where we can test this one out. So let's run the test first, but I also kind of want to show you how this one works in the debugger as well. I think it's just really important to understand, you know, how these methods are functioning. So let's start the test first. Make sure that we actually have this working properly. I can see that the geometric sum tests still passed. The 2 reversed tests, however, don't look like they're passing. So what mistake did I make? It's passing for some of them, I can see. Is it not passing for, so that's even, but it's not passing for odd valued ones. That's interesting. So to me, that suggests that there must be a problem with my base case, perhaps. Am I stopping too soon? So if it's odd, let's think about what's going to happen here. The array length, if it's 3, for example, and the index is 3 divided by 2, would actually only be 1 because it's integer division. So if the index is 1, it's not going to get swapped. It's not going to do the swapping. So maybe let's just try to take the equal sign off and see if that fixes the problem. No, that made it worse. That made it worse. Okay. Let's think about this for a second here. I'm going to run this again and try and see if I can examine the result and see if that can give me any information. Oh, did it make it worse? Actually, when I took the equals off, I was looking at the wrong tests, wasn't I? Let's try that again. Close these tests. Oh yeah, taking the equals off did have the intended effect. I believe what was happening is that it wasn't copying the middle value over when but only when the array was an odd length. It would have done the swap of the first 2 and the last 2 values, but then there would have been a hole here in the middle. That's what I expect was happening before. My base case was a little off. That's okay. We make mistakes all the time. This is a nice example, though, to see that, okay, this is really copying the loop, you know, pretty closely, right? We can see that the condition is very similar. We can see that the interior of the loop is almost exactly the same. We just have the recursive call down at the bottom to make the end. And then all the stuff that just happens one time, right? Again, we can see that happens in the non-helper method. In fact, let's go ahead and show that. I want to set a breakpoint and maybe debug one of these guys. Here we are. Here's my array. You can see the values 7, 7, 7, 93, 11. This is the stuff that's only going to happen once. That's what we're at right now. We're not doing any recursion yet. So it's going to make a copy of the array, It's going to check to see if the length is greater than 0, which it is, and then it's going to kick off the recursion starting at index of 0, passing in the original array as well as the currently empty array. You can see it's currently empty, but we eventually will be filling that up as we get through our recursion. Okay, so first thing we're going to do is check our base case. Have we gone past the middle of the array yet? We have not. So we jump down, we do some recursion. We're going to copy some values over. There we see our first values getting copied. It took the 11, copied it to the front, took the 7, copied it to the back, so that's good. We have more recursion to do, so we're going to keep going. Now it's going to take the 4, the values at position 4 and 3. Here we go. So there's the 93 and the other 7. And this is what I was talking about before, right? My base case before was written in such a way that this little hole would have been left here with the 0. But because of the way that I rewrote the base case, oops, we can see that once this is finished, shoot, I kind of hit the wrong button there. Sorry about that. But because I fixed the base case, once we step through to the final round, that 7 actually does get copied, and we can see that this now exists as a reversed version, and our original remains untouched. Alrighty. I believe there's just one more problem for us to do, which is called the greatest common denominator. So this is something that is used often in math class. If I'm trying to find, greatest common divisor. I'm trying to find the largest value that goes in evenly to two numbers. And there's actually a very well-known recursive definition for this problem. We gave you the iterative version, which is very similar to the proposed recursive version. You can see we use a while loop here. While q is not equal to 0, then we're going to take the modulus, and then I think what's important to notice is that q and p kind of switch places a little bit, right? So p becomes q via the use of a temp variable, and then q becomes p mod q. So the next time through the loop, p and q are going to have different values. Every time through the loop, they're going to have different values. Once we get to the end, we're going to find that as q goes down, p goes up, 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 and that's going to return our value of p. This is another example of some somewhat simple recursion. I don't think we need a helper method here. I don't think we need anything other than to kind of go through the motions of this problem. We can actually see this is a pretty clear description of what we need to do. The greatest common divisor of two numbers, p and q, is equal to q if p mod q is equal to 0. So the first thing we need to do, that's our base case right there. If p mod q is equal to 0, then we know what our answer is. It says our answer is q. Right? If p mod q is equal to 0, then the greatest common divisor is q. Otherwise, it is equal to the greatest common divisor of q and p mod q. So there's the recursion. Greatest common divisor is defined as the greatest common divisor. That's recursion. So to finish this up, we'd say return greatest common divisor of q and p mod q. This is actually students can overcomplicate this problem. I've seen students overcomplicate this problem before. It's actually very straightforward. I think it's not intuitive. So I would say that if I sat you down and said, hey, try to figure out what the greatest common divisor is for a number, you probably wouldn't try to do it this way, at least not without some hints and some pushing in the proper direction, right? But this is a very well-known recursive algorithm, a very sort of famous recursive algorithm. That's kind of why we wrap up the studio with it. Let's go ahead and run the unit tests and make sure that our solution is working properly. They should hopefully all pass now. This is the final problem of the studio. There we go. All of our unit tests have passed. So on the homework assignment, I think it's very important to understand what kind of recursion you're getting into. Is this a simple recursive problem, or is it a divide and conquer problem? Do I need a helper method? A lot of the parts of the assignment actually give you some hints about that. For exponents, you actually don't really need a helper method. For array sum, it's actually strongly suggested that you do. For dragon curves, you actually don't need a helper method. It's very doable without a helper method. And then for max path length, this is actually going to be an example of a divide and conquer problem. So yeah, definitely keep those ideas in mind as you're working on these problems. And that's going to do it for our Studio 6 review. I hope you all have a great weekend. I'll see you in class next week.